So last we discussed was about the galvanic cells. Now today we'll discuss about the electrolytic cells and conductometric titrations and all. Let's see now. First, let us go with the fact of electrolytic cell. Electrolytic cells. In electrolytic cells, we will be discussing mainly about Faraday's laws. Now, according to Faraday's laws, whatever the weight of the deposition on cathode or anode is always proportional to how much amount of charge that you are sending, and this would be termed as first law. Okay, according to first law of Faraday's, this is what we need to check. And W will be also proportional to I into T, where Q, which is charge, can be written as I into T. And if you remove the proportionality, you will get a proportionality constant Z into I into T here. Okay. Here Z is called as electrochemical equivalent. Electrochemical equivalent. Okay. So electrochemical equivalent mainly depends upon the property of the solution. Correct. And what happens at cathode here? Suppose if we take various cases, right? We need to understand what would happen at cathode. So, sorry, let me write down first the units of this one. Units of Z would be equal to gram per coulombs. Okay. Now, imagine there is some reaction happening at cathode like this. Half of O2 plus 2 electrons plus H2O is converting into 2OH minus. Okay. So you would notice by moles here, correct? It is half mole, half mole. This is 2 Faraday because 2 electrons is nothing but 2 Faraday. This is 1 mole and this is 2 moles, isn't it? This is by moles. Okay. And if you notice, the valency factor of O2 is actually 4 because for one O2 molecule, it will convert into 2 O2 minus. So number of electrons transferred are 4. Here. So which means now if you notice that if the number of equivalents are 4, half into 4, that makes it 2 equivalents. Equivalence wise it is 2, and this is 2 Faraday here, and you will notice that H2O number of equivalents, if you compare here, uh, it is same one molecule here, one mole here, and suppose if at all you multiply everything with 2 here, so what do I get here? So I'll get this as 2 equivalents, 2 Faraday, and here also I'll get it as 2 equivalents and 2 equivalency. Correct? And now, which means if you notice the number of equivalents wise here, correct? Because this is half into half moles into 2. So this should have 2 equivalents. If this is 2 equivalents, we need to have 2 equivalents of this, 2 equivalents of this, and 2 equivalents of this, which is law of equivalence, isn't it? And that is exactly what we are trying to understand, that if you know the equivalents of one particular compound, the number of equivalents will be same for all others. Similarly, imagine one example happening at cathode, something like CH4 gas plus 8 OH minus is giving CO2 plus 8 electrons plus 6 H2O liquid. Here also, if you notice by moles, it is 1 mole, 8 moles, okay, 1 mole, 8 moles, and 6 moles, correct? And valency factor for carbon in this case, valency factor is 8. Why? Because from from minus 4, it is changing to plus 4. So the number of electrons transferred are 8. Okay. So therefore, if this is 8 equivalents, this should also be 8 equivalents, 8 equivalents, 8 equivalents, and 8 equivalents. Isn't it? Again, this is by law of equivalence. Okay. So you can notice this number of moles of Faraday by number of moles of CH4 is 8 is to 1. 8 is to 1. So number of Faraday will be 8 times the number of moles of CH4. Clear? And 1 Faraday is equal to, see, 1 Faraday is equal to 1 equivalent weight. So then 1 Coulomb will be equal to equivalent weight by 96500. Clear? 96500. And that will be nothing but Z, because this is the weight that got deposited, isn't it? So therefore, the same formula I can modify. Now the same formula I can modify as uh, mass, or the weight that is getting deposited in grams, will be equal to Z into I into T, where Z can be written as equivalent weight of the substance divided by Faraday F into I into T. So I request you to remember it this way: E by F into I into T, which would be more useful while solving questions. Got it? So remember this as the first law formula for Faraday. Now, if you notice the second law is about having things in series. Okay, so if you have connected cells in series, then uh, you would see there will be certain amount of depositions at various places. Suppose if this is how in series we have connected few cells. So imagine this is this, here there is one cell, here there is one cell, here there is one cell. Okay. So in these cells, we have various depositions. Here at cathode or anode, you can compare any one. So at cathode, let's say W1 is deposited here, W2 mass is deposited here, W3 mass is deposited here. Respect to that element or compound, we have Z1, Z2, Z3, and so on. But the charge in a series will always flown will be same, correct? So this will be the charge. So in that case, Faraday's second law tells us that the ratio of the weights deposited will always be equal to ratio of their electrochemical equivalents. And we learned that electrochemical equivalents are directly proportional to equivalent weights. So therefore, W1 by W2 is equal to E1 by E2. Okay. So this is another important part which we need to know from second law. Right? Now, how the questions are framed, let us see. Usually, first you would be asked about identify the number of Faradays. Any conversion to any conversion you should know. There was one standard JE question which was asked: 61.5 grams of nitrobenzene, nitrobenzene is converting into aniline, is converting into aniline. Okay. We need to calculate number of number of Faradays, number of Faradays required, number of Faradays required. You just need to figure out the oxidation state on both the cases. NO2, here oxidation state is +3, and NH2, here oxidation state is -3. So the number of electrons transferred between them is 6. So that means 6 Faraday of electrons are transferred. Okay. 6 Faraday of electrons are transferred. And you know that 61.5 grams of nitrobenzene is same as writing as half mole of nitrobenzene. So which is 0.5 moles of the nitrobenzene here. Clear? So therefore, if 1 mole requires 6 Faraday, half mole, 0.5 moles require 3 Faraday charge. This is one straightforward question that will be asked. Okay, so be careful with that. Yeah. Next, if you have different solutions in which we need to find out which one will be the uh, anode, what will happen at cathode, and what will happen at anode. Okay, so we'll start with the first one: electrolysis of water. Electrolysis of water, H2O. Okay. In electrolysis of water, there are two things we need to understand. What is the anode and what is the cathode, E naught value. E naught value where H2O is getting oxidized to O2 will be minus 1.23 volts. Okay. While E naught of H plus and H2 is 0 volts, and E naught of H2O to H2 is minus 0.83 volts. Okay. See, if you have a very poor, if you have a pure water that is distilled water, then it's extremely bad conductor. So you will not see much of depositions. So that's why whenever electrolysis of water is being done, then we use very dilute H2SO4 is added. Okay, very dilute H2SO4 is added. On adding such dilute H2SO4, now we will see at anode there is one more reaction that can compete, that is SO4 2 minus can also get oxidized to S2OA 2 minus, and for that the E naught value is minus 1.96. Now notice between these two reactions here, between these two, the amount of H plus is extremely less and amount of SO4 2 minus is very very small in this case. Okay. So what is that we expect in water is mainly this one and this one. These two are the reactions which we'll expect. So now you notice what is the anode reaction. Anode reaction is H2O liquid converting into half O2 gas plus 2 electrons plus 2 H plus aqueous. While cathode reaction, cathode reaction will be 2H plus, sorry, 2H2O 2H2O plus 2 electrons converting into H2 gas plus 2 OH minus aqueous. So if we write the overall reaction here, it will be 2H plus 2 OH minus is giving 2H2O. Got it? So, sorry, H2O is, this is the reverse of it. Right? So overall reaction is H2O liquid is converting into H2 gas plus half O2 gas. And how many Faradays are required in this case? 2 Faradays. This is important part. That for every 2 Faraday charge, I'll get 1 mole of hydrogen and I'll get half mole of O2. Half mole of O2. Okay. I hope this is clear, everybody. The electrolysis of water or dilute H2SO4, right, with a very small composition. This is what will happen. Okay. Right. Next. Second case we need to understand is about electrolysis of aqueous NaCl. Aqueous NaCl using inert electrodes. Inert electrodes could be either graphite or platinum. Okay. Usually it is always taken as platinum. So based on that, at anode, what are the reactions that are competing? At anode, the reactions that are competing are E naught H2O to O2, which is minus 1.23 volts, and E naught of Cl minus to Cl2, which is minus 1.36 volts. At cathode, what are that are competing here? At cathode, the reactions that are competing is E naught H2O to H2, which is minus 0.83 volts, and E naught Na plus to Na, and that will be 2 minus 2.71 volts. Okay. Now, there is a concept called overpotential. Overpotential, or also known as bubble potential. Due to overpotential, although this value is smaller, it will be slightly more feasible as compared to that of water getting oxidized. And here, obviously, the difference is quite high. So water is only going to get reduced. So the overall reaction would be like this. Overall reaction would be 2H2O liquid plus Cl minus, 2Cl minus is converting into H2 gas plus Cl2 gas plus 2OH minus aqueous. Okay. So this is how industrially chlorine gas is also prepared as well as H2 gas is also prepared. Got it? Here. And this is known as chlor-alkali process. Chlor-alkali process. Okay. So what we learn from here is for every 2 Faraday now, again same logic here, for every 2 Faraday, 1 mole of H2 gas will be released and 1 mole of Cl2 gas will be released. Got it? So keep this in mind due to a concept called overpotential. Okay. This is what would happen. Okay. You would not be asked much details about overpotential and all. So don't waste much energy there. Just understand that due to that concept, this is what will happen. Okay. See, one thing, one note we need to remember is this. If cathode is made up of mercury, then Na plus aqueous will get reduced. Will get reduced. Okay. So that is Na plus aqueous plus one electron will give you in the presence of mercury electrode will become sodium mercury amalgam. Okay, so sodium mercury amalgam. But this is theoretically not feasible, correct? So which means NaHg liquid, correct? Sorry. First, let me write on this way. Sodium plus mercury, if I write it this way, this is not theoretically feasible. So which means these two will be always appeared in a combined state. Hg, Hg liquid will be in a combined state. So that is NaHg liquid where delta G is negative. So because this is highly negative, this is a feasible reaction for formation of amalgam. Okay. Clear? So generally, if I give you 10 grams of sodium in amalgam, if this terminology is used, it means I have 10 grams of sodium in 100 grams of total mass of amalgam. Okay. Out of which 90 grams will be of mercury. So I guess this part is clear, everybody. This will be with aqueous NaCl. Third one is for copper sulfate aqueous solution. Copper sulfate aqueous solution. First, using inert electrodes. Using inert electrodes. So that means cathode is also inert. Cathode is also made up of platinum. Anode is also made up of platinum. Okay. So at anode, what you would notice is there are two reactions competing again. H2O2O2, which is minus 1.23 volts, and SO4 2 minus 2, S2O8 2 minus, which is minus 1.96 volts. Right. At cathode, two reactions are competing. E naught Cu2 plus 2 Cu, which is plus 0.34 volts, correct? And E naught H2O2 H2, which is minus 0.83 volts. Correct? So these are the ones which are competing. So definitely here it is pretty clear that uh, here copper will get reduced and here water will get oxidized. So using that overall reaction will be copper 2 plus aqueous plus H2O liquid will give us half of O2 gas plus 2H plus copper solid. Again, this is for 2 Faraday charge. For 2 Faraday charge, this much will be the reduction which is observed. Okay. Now, there are two to three important things we need to understand. Initially, the solution is intense blue color because copper sulfate is a blue color solution. Okay. intensity of blue color decreases over the time. Intensity of blue color decreases. That is important part which will be asked in exam. Next, pH, if you notice what is happening, the H plus is increasing, so therefore pH value decreases over time. Decreases over time. Third thing you will notice, correct? Uh, yeah, this is mainly used for electroplating of copper. Electroplating of copper, right? So these three are the important points you need to remember. Okay. So suppose if we have only copper electrodes here, both sides we have copper electrodes. This was case one using inert electrodes, but this time we are using only copper electrodes. Cathode is also copper, anode is also copper. So at anode, now there are three reactions competing. At anode, three reactions competing. One, H2O changing to O2, which is minus 1.23 volts. Next, SO4 2 minus changing to S2OA 2 minus, which is minus 1.96 volts. And then copper itself is also going to get deposited, dissolved, and that is minus 3.1. Next, cathode side, we have E naught, copper 2 plus getting deposited, which is 0.34 volts, and water, which is going to get reduced as minus 0.34 volts. So you will notice that this one and here this one. One is cathode, one is anode. These two are the ones which will get reduced. Okay. Now, in this case, whenever there is copper getting reduced, right? So we can use this especially when you have an impure copper on the anode side. Okay. So suppose if you have in electrolysis this side of the anode, and here if you have a cathode, and this is impure copper, and this is pure copper. We can use this impure copper to melt, and here it will get deposited. Along with impure copper, we might have various metals. We might have iron, zinc, tin, silver, maybe gold, some platinum. We have some antimony, we have tellurium, we have selenium. Lot of metals will be present along. Correct? Now, what you would notice is that if you compare the elements like this iron, suppose E naught of Fe2 plus, sorry, Fe to Fe2 plus, correct? Its value is around 0.44 volts, and E naught of zinc to zinc 2 plus, that is around 0.78 volts. Okay, but these are all in small quantities, right? Small quantities. Clear? So what will they do? They will they will all get dissolved. So metals which get dissolved, metals which get oxidized or dissolved includes iron, zinc, tin, to some extent lead, nickel, cobalt, chromium, and so on. Okay, and metals which remains as you know metals only, or which we call it as anode mud. That means they'll deposit just below here. At this position, they'll start getting settling down. This is called anode mud. On the anode mud, that includes okay, uh, gold, platinum, silver, selenium, tellurium, correct, and antimony. These are the metals which you will find, correct. So remember, this question could be asked: which will get oxidized and which will remain as the anode mud. So these are the elements which are found in anode mud. Okay. Now, what you would notice, since the copper sulfate always have the same amount of copper in the solution, intensity of blue color remains same, almost same. So it is not going to change. Correct? Second thing, pH remains same. Clear? And this is also used for electroplating of copper, electroplating and refining of copper. All right. Very, very important area, everybody. Please remember these two parts. Okay. What with inert electrodes and what with copper electrodes. Okay. Because this is the same theory we will learn once again in metallurgy. Correct. So you should be aware of it. What will happen to these cases? Then one of the typical examples which have been asked, in JEE a lot of times is coal-based electrolysis. Although you must have learned in organic, so do remember what are the reactions that takes place. Okay. See, coal-based electrolysis is going to happen at the inert electrodes, and on inert electrodes at anode, you take a carboxylate salt like acetate CH3CO minus, and that would give us CH3CO dot plus one electron. Got it? And this would eventually become CH3 dot plus CO2 plus 1 electron. While at cathode, you will notice that 2H2O liquid plus 2 electrons will convert into H2 gas, H2 gas plus 2 OH minus. Since OH minus is increasing, pH value will increase. pH value will increase in the overall reaction. So overall reaction you'll notice that 2H2O plus 2 moles of CH3CO minus is able to produce C2H6 gas plus H2 1 mole of gas plus carbon dioxide 2 moles of carbon dioxide, clear, plus 2 moles of OH minus. Okay. So this is the overall reaction which you will notice. Done. So I hope all of you got an idea about what type of questions that could be asked from Faraday's laws. And mainly the electrodes, you need to be very clear about what would happen. Okay. 1 minute. I think I forgot to discuss about concentrated form or right. If you have uh, electrolysis of electrolysis of concentrated H2SO4. Concentrated H2SO4 at anode, you will have very less quantity of water to compete with, to O2, giving minus 1.36 minus 32 volts here, while E of SO4 2 minus to S2OA 2 minus here. This we learned earlier, the value, how much we had here, the value shared is minus 1.96, and this is 2,3. Now, although this value is less compared to water, because the quantity is less here, majority of the form will be this one. A very small quantity will happen here, but majority of the form will be this one. Okay. At cathode, there is no such issue. At cathode, we will have a similar case. H2O to H2 here will remain minus 0.83 volts, and that will dominate. Only at anode, the reaction will be like this. SO4 2 minus of 2 moles will convert into S2OA 2 minus plus 2 electrons. Okay. Now imagine this, if you get a deposit of this one, I mean you get a solution of S2OA 2 minus, then by chance if you add it to the heavy water, correct? If you add it to heavy water, then you will get 2 moles of, first you will get this way. First one will become DHSO4 minus, DHSO4 minus plus DHSO4 minus, then D2 SO5, D2SO5. This is the first thing you will notice. Plus OD minus here. And this D2SO5 on further hydrolysis will convert into D2SO4 plus D2O2. Okay. And same way, DHSO4 minus plus D2O if you add again. So this would again become, you know, uh, this would again become D2SO4 plus OD minus. So basically you will get 2 moles of D2SO4 and 1 mole of D2O2. Got it? And this is how H2O2 is also prepared or D2O2 is also prepared. So remember these reactions. Got it? Next. The third part of uh, electrochemistry is about conductance, conductivity, conductivity, and uh, that's it. Conductivity, resistivity, all of these are under same thing. Okay. See, there are four types of conductors generally: metallic conductor, electrolytic conductor, semiconductors, and insulators. Okay. So order of conductivity will always be equal to metallic conductor, which is way higher compared to that of electrolytic conductor, which is greater than that of semiconductor, which is way greater than that of insulators. Insulators, okay. Insulators are the least conducting things, okay. And whenever you are using electrolysis, we always use DC current. So keep this in mind. We cannot use AC current. We always have to use DC current, okay. But when when we measure when we measure resistance or conductivity, then we have to use AC current. Then we have to use AC current. Now, to remind you, the definitions of all the terms related to resistance are this. First, if you have a length L of a wire or a rod, and then if this is the area of the cross section A, then resistance will be rho into L by A. Okay. Rho is called as resistivity or specific resistance. Clear? And you know that R and G, okay, R and G, which is called as the G or C. In NCERT, G is used as conductance. These two are extensive properties, while rho and kappa, these are intensive properties. Now, what is G and kappa? See, G or C, this is same, which is nothing but 1 by R, which we call it as conductance. This is called as conductance. While kappa is 1 by rho, right, which is called as conductivity or specific conductance. Clear? Well, there is one more term known as G star, which is equal to L by A, okay, which we call it as cell constant. And also this is depending on dimensions, so this is also extensive. So wherever you write VT, right, conductivity, resistivity, or specific word is used, specific conductance, specific resistance, they all will become intensive. Anything which is a general definition like this, they are all going to be extensive. Okay. Now, if we do the same thing in electrolytic cells, right? If this is an electrolytic cell like this, then you need to check out how much amount of liquid is present, correct, between the plates. So this is that area between the plates. Between the plates, how much amount of volume that you have covered, that becomes important in this case. And what is the area of cross section of this plates? So if the area of cross section of the plate is A and the distance between them is L, correct? So in that case, 1 by R here. Acha, this L always had to be perpendicular distance. Sometimes questions are framed with a slanted height. You need to take its component. L should always be perpendicular distance between two electrodes. Between two electrodes. A represents area of cross section of electrodes of dipped amount of dipped part dipped part in electrolytic solution. Okay, so that makes it 1 by R is equal to kappa into A by L, and kappa is equal to L by A by R. So that is equal to cell constant divided by resistance. This will be used a lot of times while are solving problems, which is G star by R. G star by R. Okay. See, when it comes to metallic conductor, you know that on increasing temperature, resistance will increase. Correct? Because more hindrance will be there for free electrons. But in electrolytic conductor, it is exactly opposite. Okay. So it will be increasing temperature means resistance will decrease and conductivity will increase. That is a major difference between these two. Other than that, the differences I gave you in the notes, I request you to just go through it once. But electrolytic conductor, what you need to know more importantly, okay, is this, that it depends on what factors. Okay, depends on first nature of electrolyte. What is the electrolyte you are using, and whether it is weak electrolyte or strong electrolyte. That is the first thing it depends on. It also depends on concentration of electrolyte in the solution. Okay. It also depends on size and nature of solvent. Size of electrolyte and nature of solvent. Nature of solvent as in whether it is polar or non-polar. So when it comes to electrolytic conductor, a lot of factors need to be taken care of. Clear? Right. Next, usually we know that on dilution, okay, conductivity of conductivity of weak electrolytes, okay, will uh, decreases. Conductivity will decreases. Clear? Because you will have less number of ions. As the in the part here, you notice more amount of water you add here. Let's say initially we had these many number of ions. If you add more water, now the number of ions appearing will be less. So less number of ions means less amount of conductivity. Got it? So for example, if you take CH3COOH, it is a weak electrolyte ionizing into CH3CO minus plus H plus. So generally we write their degree of dissociation as alpha here like this. And you know that H plus concentration will be equal to under root of Ka into C naught. So you can notice that as the C naught value increases, the H plus value will, C naught value decreases, H plus value will also decrease. That means number of ions are decreasing. If concentration of ions decreases, which means conductivity will always decrease. Keep this in mind, everybody. Okay. But there is one factor which will increase is molar conductance. Molar conductance. that is lambda m. Well, it is defined for, uh, for 1 mole of an electrolyte in any amount of volume V. Okay, that is conductance of 1 mole of electrolyte, 1 mole of electrolyte in any volume V. Correct. Now notice this. If I get the same situation here, if I get the same situation here, but now I have to fix that number of 1 mole. So for suppose if at all I dilute this from here, I say I made a dilution. Here, let me just point out here as these are all the ions possible. These are all the ions possible, correct? But if you make a dilution here, if you make dilution here, then what we should do to accommodate more number of ions in the same plates, you have to change the size of the plates now. You have to change the size of the plates, or the dimensions of the plate must be changed. Okay. So like this, you'll have to change the dimensions here, correct? So that more amount of water can be accumulated or more amount of solution can be accumulated like this. But these are the same ions which we took it early like this. Same number of ions are present. But on dilution, what happened? You had to change this dimension to ensure that the same 1 mole is being accommodated. So there are two advantages here. First, the distance between the ions increases. That will make it more free movement for ions. Second, because it will get more space to move around. So the number of ions are same. So that will increase or improve the movement of ions, and therefore the molar conductance will increase. Got it? So molar conductance should always be used for the case where we have um, molar conductance can be used for the case where we have what do you say, same distance, clear, but the area could be different. So that's why any volume V is important, correct? The length is not changed. Length is always 1 unit. Number of moles are always 1 unit. This is the important part of the definition for lambda. Okay, volume and area can be anything that can keep changing. So G, which is equal to kappa into A by L, which is conductance. Now lambda M is the conductance. Lambda M is the conductance, which can be written as K into V by L square. Here, K into V by L square. So which means this will be G into V, because if you have to, sorry, G into, sorry, my mistake. So this is supposed to be kappa into V. Achha, what is kappa here? Kappa, which can be written as G into L by A, G into L by A into V, correct? So that is equal to G into L square into V by V only. So this will get cancelled. So therefore, uh, lambda M is equal to conductance into L square, that is equal to kappa into V. Since L is 1 unit, so that will be same as the conductance. Understood? So this is an important formula, everybody. How lambda M is related with kappa as well as with conductance. Okay. Here. Now lambda M can be written as kappa into 1 by kappa by 1 by V. Kappa by 1 by V. Okay. And now kappa by 1 by V, molarity is what? Number of moles by volume. If number of moles is 1 by V, then 1 by V is nothing but molarity. So kappa by molarity. So by dimensions, if you write down, if you notice, if molarity is written as moles per liter, correct? Then kappa, which can be written as Siemens centimeter inverse or Simon meter inverse, then we should be able to write this molarity lambda m units as ohm inverse, meter square, meter square, and mole inverse, or Simon meter square, mole inverse, or Simon centimeter square and mole inverse. These are various ways of writing lambda m, everybody. Now, to accommodate these units properly, we'll have to write lambda m is equal to kappa into 1000 by molarity when it is mole per liter, and here the dimensions would be Simon centimeter square and mole inverse. Lambda m will be equal to kappa into 1000, sorry, kappa by 1000 times of molarity if the units are Simon meter square and mole inverse. Correct? So remember which units to be used. You know, accordingly we'll have to use the units. Okay. Next. Another similar term is equivalent conductance. Equivalent conductance, which is lambda E. So since we understood lambda M, I hope that same logic, it is about one equivalent of electrolyte in one unit difference, one unit difference of electrodes and any volume V, any volume V. Okay, these are the conditions. So therefore, lambda E will be equal to kappa into 1000 divided by normality this time. And the units will be Simon centimeter square and equivalent inverse. Just like mole inverse, it will be equivalent inverse. That's it. That is the main difference between these two. Okay. Lambda M and lambda E are intensive properties. They are intensive properties here. And lambda M by lambda E will be equal to N by M, which is equal to valency factor, which implies lambda M is equal to valency factor into lambda E. Another important formula, everybody. Okay, here. So which shows that lambda M value will always be greater than or equal to lambda E. Okay. Now, lambda M is identified, the variation of lambda M is identified with respect to the concentration, okay, as two major graphs. One is this way, the other one is this way. Now, this one is for strong electrolytes and this one is for weak electrolytes. Got it? So from here, what are the conclusions we can draw? On dilution, lambda M or lambda E will always increase. Okay? Clear? For both weak electrolytes and strong electrolytes. Okay? Next. These values are lambda M infinity or lambda M naught, where they are touching almost at zero concentration. So lambda M can be written as lambda M naught minus some constant A into root C. And this is known as Debye-Huckel's equation. Debye-Huckel's equation, everybody. Okay. The A value depends on, right, solvent nature and temperature. Solvent and temperature of, uh, for example, temperature. Well, and electrolyte charge or valence. That means if you notice the A value for MgSO4, it will be greater than CaCl2, it will be greater than NaCl. So you could observe first is the charge dominant, +2, -2, +2, -1, +1, -1. Okay. So lesser the charge on it, lesser will be the dominance. Okay. This can also be written as a graph like this, that A versus uh, here lambda m versus here root C. If you get three graphs like this, so the first graph will be for MgSO4, second will be for CaCl2, and third would be for NaCl. Okay, because more negative slope, right? More negative slope, which means it will be for NaCl, and more positive slope, which will be more for, I mean, more towards the positive slope means it will be for MgSO4. Okay. The next thing we need to understand is Cole-Rush law. Cole-Rush law. This is about migration of ions, independent migration of ions. So where it shows that uh, if lambda m of a particular ion K plus in K2SO4 solution is observed, and lambda m infinity of K plus in KCl solution is observed, will both be same, So that means lambda m of K plus value coming from K2SO4 will be same as lambda m of K plus value coming from KCl. So as long as the ion is same, whether you get it from solution X or solution Y, the value would be same. Right? Therefore, we can always write it this way. Lambda m infinity of K2SO4 can be written as 2 times of lambda m infinity of K plus lambda m infinity of SO4 2 minus. Achha, you can write either as infinity or as naught. Both of them are same. Okay. Similarly, I can write lambda m naught of Na2SO4 is equal to 2 times of lambda m naught of Na plus lambda m naught of SO4 2 minus. If you are able to write this, that means it is following Cole-Rush law. Okay. See, you got to understand what is the relation between lambda m infinity and lambda m naught and lambda e naught of any particular compound. For example, let us take K2SO4 dot Al2SO4 thrice dot 24H2SO4. This is potash alum. So if I take potash alum, what all ions it can give? It will give 2 moles of K plus, it will give 2 moles of Al plus 3, and it will give 4 moles of SO4 2 minus. Okay. And valency factor is 8 here. Valency factor is 8. So what I can write? 8 times of lambda m naught, lambda e naught, because go back to the definition here, lambda m can be written as valency factor into equivalent conductance. So that's what I'm writing. Valency factor lambda m naught will be of the salt of alum will be equal to this of alum. Okay. And that would be equal to 2 times of lambda naught e of K plus 2 into 3 times of lambda naught e of Al plus 3. That 3 is multiplied because it is a valency factor for aluminum. Plus 4 into 2 times of lambda e naught of SO4 2 minus. Okay. My request is please learn to write this thoroughly. Okay. If I write it 2 into lambda m times of A naught plus 2 into lambda m of Al plus 3 naught plus 4 into lambda m of SO4 2 minus. And that when you write in terms of equivalent conductance, this is what you will get. Okay. So therefore, lambda E naught of alum will be equal to this 8 need to be divided. So lambda m naught k by 4 plus lambda m naught uh, 3 by 4 3 by 4 of Al plus 3 plus lambda naught E of SO4 2 minus, right? This is how. So this divided by 8, this divided by 8, and this divided by 8. So when you do that, this is what you would get. Okay. Got it? Biggest advantage where we will get is here. So for weak electrolytes, for weak electrolytes, you can say H HAC as a weak electrolyte if it becomes AC minus plus H plus. Clear? Then we can write this as C naught into 1 minus alpha, C naught alpha, and C naught alpha. Okay. So from there, I can write K K equilibrium or Ka is equal to C naught alpha square minus 1 by alpha square. And alpha is always equal to lambda m of HAC divided by lambda m naught of HAC. It is always less than or equal to 1. Okay. So therefore, K can be written as C naught into lambda m by lambda m naught whole square by 1 minus lambda m by lambda m naught whole square. This formula will always be useful everybody. Okay. Now suppose if I want to find out ionic product of water in terms of kappa, lambda m and lambda m naught. Okay. So kappa of water, that is conductivity, conductance or specific conductance of water can be written as KH plus KOH minus because conductance is also additive. So lambda m of H plus can be written as KH of H plus into 1000 divided by concentration of H plus. Okay. Similarly, lambda m of OH minus will be kappa of OH minus into 1000 divided by concentration of OH minus. Okay. Now, concentration of H plus can be written as under root of Kw because Kw is something which we know, right? So we can write this as KH plus into 1000 divided by under root of Kw. And here also I can write KOH minus into 1000 divided by under root of Kw. Correct? Now, K of H2O can be written as lambda m of, if I just add these two, so what would I get? Lambda m of H plus, right? Lambda m of H plus plus lambda m of H plus plus lambda m of OH minus that whole into under root of Kw, which will come out as common divided by 1000. This is what we are getting. Okay. So therefore, Kw will be equal to 1000 times of kappa of H2O divided by lambda m of H plus lambda m of OH minus whole square. So that's how we can find out the Kw value. Usually Kw values always use this way. Okay, clear? Next thing, one very important aspect you need to understand is for sparingly soluble salt, for sparingly soluble salts, lambda m naught is always equal to lambda m. Okay, clear? So whatever the concentration will be, whatever be the amount that is getting dissolved is completely 100% ionized. Got it? For example, if I ask you, write the expression for write expression of lambda m of AgCl, okay, lambda m of AgCl in terms of solubility S. The answer is very simple. Here, lambda m will be equal to kappa of AgCl into 1000 divided by molarity, right? Molarity is nothing but concentration S. That's it. Now you know that AgCl will be ionizing as Ag plus plus Cl minus, which means I can write it as S, and S square will be equal to Ksp. So here I can write cap of AgCl into 1000 divided by under root of Ksp. Simple. Okay. So for sparingly soluble salt, remember it becomes very easy. You just have to write that. You don't have to worry about that concentration term. It is always going to be equal to solubility. Okay. I hope this is clear. I have added a lot of questions, based on uh, conductometric conductivity cells. Please go through that questions. Should be useful. Anyways, we'll do some more questions from PYQs. First, just let me cover up all the theory part. Next thing we need to understand is about conductometric titrations. When it comes to conductometric titrations, you need to understand what are the cations and how much is their lambda m naught value. Okay, in aqueous solutions, everything is in aqueous solution. H plus have exceptionally high value, which is 350, and Na plus is around 50, K plus is around 73.5, and calcium 2 plus will be around 119, right? Mg2 plus is around 106, while NH4 plus is around 73.4, and Ag plus is around 61.92, and Ba2 plus will be around 107.23. Okay, these are various values for cations. Okay, if you have a cation of complexes, they will also have a good amount of conductivity, like cobalt, H2O 6 plus 2. For this, the conductivity is around 102. While when it comes to anions, lambda m naught value, if you compare, again OH minus exceptionally high, around 200. Cl minus is around 76.3. Br minus is around 78. Okay. CH3CO minus is around 40.9. SO42 minus will have 160. ClO4 minus is around 68. Clear? F minus is around 55. Correct? And NO3 minus is around 71.4. Okay. It's not like you'll be asked the values, you just need to know how to compare them. Okay. Generally, I can say that lambda m naught for divalent is greater than monovalent, except for hydrogen. Except for hydrogen, that is an exception. This is not valid for H plus and OH minus. Okay. This is due to the hydrogen bonding. H plus and OH minus will have very strong hydrogen bonding with water, because of which the ionic mobility is extremely high. Okay. So titrations, when we do, how does it change? Let us see. If you perform titrations, the first titration we'll perform is strong acid and strong base, typically HCl and NaOH. Okay. So when you perform this titration, how does the graph varies? Check it out. So for lambda m, as we keep adding the volume of NaOH from the burette, correct? The value changes like this. It will keep going down and then it will increase. Got it? Here, basically, H plus concentration is decreasing, Na plus is increasing. That is the reason why this entire region has decreased amount of conductivity. Now here what is happening is Na plus OH minus concentration is increasing now, correct? And Na plus concentration is not changing. Cl minus concentration is not changing. Got it? So we are saying, sorry, Na plus is increasing. Na plus is increasing. OH minus is increasing, and Cl minus is not changing. This point is the end point or equivalence point. So at this equivalence point, you would see this is that equivalence point. Below that, before that, it will be decreasing. After that, it will be increasing. Here, the decrement is because H plus is being lost and it is replaced by Na plus. Here, the number of ions are increasing. Na plus is also increasing. OH minus is also increasing, by which you will have more amount of conductivity. Got it? Second iteration is about weak acid and strong base. Weak acid and strong base. In case of weak acid and strong base, like something as simple as CH3COH, titrated with NaOH. In that case, if you compare lambda m, initially there will be small decrement here, very small decrement. This is because of H plus being lost. Same logic here, H plus is being lost and Na plus is being gained. Then afterwards, it will be increasing here. It will increase, reach to a value here, and from there, again, it will start increasing. Right? Now, at this point here, it is getting more ionized. AC will get completely ionized as AC plus, sorry, AC minus and H plus. Because so more ions. In this region, you'll have more ions. Due to more ions, it is increasing. And here there is no reaction. Here both OH minus concentration is increasing and Na plus concentration is increasing. That's why again it will increase. Now this point is the end point. So remember, this is the graph that you will be given. Okay. Here everybody. So if sometimes this part is not given, so it is still you can take it as correct. That means initially there was no ionization at all. So you can directly start from here and go like this. Correct. The third titration which could be asked is for weak base, weak base plus strong acid. Okay. Here also it is the volume of base added. Okay. Now in this case also the graph would be exactly same. Okay. So lambda m here, you'll notice this is the volume of HCl added. Volume of HCl added. Initially it will decrease, then it will start increasing. After that reach to a neutral point. From there it will increase again. Correct. So here in this place, OH minus concentration is decreasing and Cl minus concentration is increasing. In this case, more ions are forming. That's why it is increasing. At this nature, H plus is increasing as well as Cl minus is increasing. So that's why it is drastically increasing there. Okay. So this is the value which you will notice. So if the graph is almost given like this, then also you can accept it correct, considering initially there is no ionization. Okay. So if it is about weak acid and weak base, fourth one, weak acid and weak base. Like I have CH3COOH plus NH4OH. If this is the case, now you will see lambda m versus volume of NH4OH being added. Then again slight decrease here. From there it will be increasing. And after that, it will hardly change. You will hardly see any change because Here you are adding NH4OH, which is not an electrolyte. I mean, it is an extremely weak electrolyte. So because of that, there is no change, although it is added, but there is no change in the lambda M value. Okay. Next, fifth one is a titration between weak acid plus strong acid plus strong base. So there is a weak acid, weak base. Like I have HCl plus CH3COOH added with NaOH. So if this is the case, so initially the strong acid will get completed and then the weak acid will start. So that's why initially it will decrease, reach to first equivalence point. From there it will increase, reach to second equivalence point. From there it will increase again. So this is EP1, this is EP2. Got it? So here also in this case H plus is decreasing, Na plus concentration is increasing. Here ions concentration increases. Here OH minus concentration increases. Okay. These are the reasons for this graph. Lastly, last graph is about precipitation. AgNO3 plus KCl precipitation. So in case of precipitation, in most cases, right, precipitation reactions, in most cases of the precipitation reactions, the conductivity of any solution like Ag plus and K plus is almost the same. Lambda M of Ag plus ions will be almost same as that of K plus ions, almost. Okay, that is an assumption on which it will run. So since it is same, initially you are just replacing Ag plus is going, K plus is taking up. So there is no change. Once it reaches to a point where the precipitation is completed, then after that it will start increasing. Got it? This is how it will take place. So for any precipitation cases, guys, this is how we need to understand. Okay. So I hope these graphs are clear. Conductometric graphs only, as per JE syllabus, only these 6 graphs are there. You would be asked. So learn these graphs thoroughly. Okay, what would happen here? Okay. Last thing we need to focus is about corrosion. See, if iron is getting corroded, it is called rusting. Correct? And if silver is getting corroded, it is called tarnishing. But the idea is the same. It is getting corroded. So in corrosion, always there are two things that should be present. One is oxygen and water. Oxygen comes from air and water comes from moisture. Okay. So anode reactions that will take place is iron getting oxidized to Fe plus 2 electrons. And E naught value for that is 0.44 volts. And at cathode, you will see half of O2 plus 2H plus. This H plus is coming from the acidic medium in atmosphere that will accept these electrons to get into H2O. So E naught of O2 to H2O is 1.23 volts. Okay. So overall reaction is Fe solid plus half O2 plus 2H plus is giving Fe plus 2 plus H2O. So this E naught value is 1.67 volts. So this is spontaneous. So since it is spontaneous, corrosion will take place. Okay. So while writing E cell, how do we write? E cell is equal to E naught cell minus 0.0591 by N log of Fe2 plus concentration divided by H plus concentration into pressure of O2 power half. Okay. So from here you can see that if H plus concentration is increased or O2 concentration is increased or the pressure is increased, then E cell value will increase, which means more amount of corrosion can happen. Here more rusting can happen. So at high pressure of O2, you will always use to get this as corrosion. Okay. Usually what happens once Fe plus 2 is formed, Fe plus 2 has a ability to oxidize further in air. So it will convert into Fe2O3 dot XH2O. And this is what we call it as the rust. So what we call it as the rust. Okay. Clear everybody? Right. Because you are doing this in moisture here and uh, sorry, right. So Fe is getting oxidized, O2 is getting reduced here, and that's what would happen in this case here in the presence of H2O. Next, see, prevention of corrosion, right, is always an important case. How do we prevent it? Okay, so one of the simplest method is to prevent the surface of the metallic object to come in contact with atmosphere. Correct. This could be either done by adding a paint or some chemicals. Okay, usually, 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 bisphenol is added as a coat. Bisphenol coat is added for these metals. Okay, this will act like a paint. Got it? Another method which we can use, right, is add or cover the surface with another metal which is which is more reactive than iron. Okay, more reactive than iron. So that includes tin and zinc. Mainly tin and zinc are being added. Okay. So what will they do? They'll sacrifice over the iron. So they will when it comes to iron will remain the same, and zinc and tin, these two will be more reactive. Got it? Yeah. Sorry, not tin. I think only zinc. What? Zinc is more reactive. Zinc is more reactive. So that's why it will act like an sacrificial electrode. That will act like a sacrificial electrode. Okay. Another way we can use is metals like magnesium, uh, sorry, zinc or magnesium. This zinc or magnesium, these two can be used as sacrificial ones. Okay. Tin can also be used. Tin can also be used as it is more inert than iron. So if you put tin, the corrosion factor would be very, very less because it is more inert. It will not react on. Got it? So this is the part you need to understand, everyone. Clear? So last thing we have is about batteries. Correct? So tomorrow we'll have a discussion on that. Okay?